Hi there, welcome to this Alchemist Chemistry video looking at a bonding and structure exam style question. Now, recent experience has shown me that a lot of students really struggle with these sorts of questions where you're given unknown substances and information about them and you have to determine the type of structure and bonding present. So I want to show you how to tackle this sort of question so you can get maximum credit in the future in this sort of scenario. Let's begin by looking at substance X. It has a reasonably high melting point and it doesn't conduct electricity as either a solid or as a liquid. This is indicative of a giant covalent lattice structure, akin to something like diamond or silicon dioxide. How do we know that? Well, firstly, the high melting point is down to the fact this giant covalent lattice structure has many strong covalent bonds throughout that lattice structure that require a large amount of heat energy to overcome, hence the high melting point. And because it has no delocalized electrons within that structure, all of the electrons are involved in the covalent bonding and being shared between the nuclei of atoms, there are no free moving delocalized electrons anywhere in the structure, so it cannot conduct electricity, is either a solid or a liquid state, and therefore it must be a giant covalent lattice structure. Okay, now let's look at substance Y. Substance Y also has a really high melting point. Actually, it's even higher than substance X. It doesn't conduct electricity when it's a solid, but it does when it's a liquid. So what could it be? This time, it's a giant ionic lattice structure. How do we know that? Well, first of all, let's talk about that melting point. Inside that giant ionic lattice structure, there are many strong electrostatic forces of attraction between oppositely charged ions. These are known as ionic bonds. It takes a lot of heat energy to overcome those attractions, and therefore it has a high melting point. It doesn't conduct when it's a solid because the charged ions are held rigidly in place by those strong ionic bonds I just mentioned. And because the charged particles, in this case the ions, aren't flowing, no current can be produced. However, once you melt or dissolve that giant ionic lattice, it becomes a liquid, if it's melted for example, then you break the strong ionic bonds between the oppositely charged ions. Those oppositely charged ions can start to move and flow around, and that generates an electrical current, and hence it conducts when it's a liquid, but not when it's a solid, because the ions are flowing in the liquid and they're not flowing in the solid. Job done. The physical properties of substance Z are very different to X and Y. It has a relatively low melting point compared to X and Y. It doesn't conduct when it's a solid, and it doesn't conduct when it's a liquid. So what could this be? This is a great example of a simple molecular or simple covalent structure. The low melting point is indicative of the fact that we're not actually breaking the strong covalent bonds within the molecules in this example. Instead, all we're overcoming is weak intermolecular forces between the molecules in this structure, causing those molecules to move apart and change the state of the substance, hence melting. So it's really important to differentiate here. We're not breaking any bonds in this example. Instead, we're breaking intermolecular forces between molecules in this structure. How do we always know that? The low melting point is always the giveaway that we're dealing with a simple covalent or a simple molecular substance and not a giant substance such as X and Y. Now, it doesn't conduct as either a solid or a liquid. Why would that be? Well, it's because the molecules have no delocalized electrons that they can transfer from one molecule to another to create that current and that flow of charged particles. Because they do not possess delocalized electrons that can move between molecules, they cannot conduct electricity, and therefore they're non-conductive in either the solid or liquid state. Last but not least, we come on to substance B. B has a relatively high melting point, and it conducts as both a solid and a liquid. What could this be? This is an example of a metal, a giant metallic structure. The high melting point is down to the fact that within that giant metallic structure, there are many strong electrostatic forces of attraction between positively charged cations and a sea of negatively charged delocalized electrons around them, creating this high melting point due to all those strong attractions throughout the lattice. The conductivity, as both a solid and liquid, is down to the fact within that metallic structure there are delocalized electrons that can freely move from atom to atom throughout the metal structure and therefore conduct a current, because of a current in physics is effectively the flow of charged particles. In this case, the flow of delocalized electrons through the metallic structure itself. And that about wraps it up, except it doesn't. A couple of bonus examples coming your way. We're which might catch you out if you weren't aware of them. Number one is something a bit like B, a metal that has a particularly low melting point, which might confuse you, is mercury. So mercury, which could be a letter here, would have a low melting point, but would conduct as a solid and as a liquid, and that would be a tricky one. So it's a metal with a low melting point. And the other one that might catch you out is graphite. Graphite is a giant covalent structure which conducts electricity. So it have a high melting point, but it would actually conduct as a solid, unlike X. So graphite, giant covalent structure which conducts electricity because it has free delocalized electrons, number one to watch out for. And mercury, metal with a low melting point. Curveballs. And that officially wraps things up. Thanks for listening, guys. I really hope this example helps you in the future with exam questions you might face. And I'll talk to you in the next Alchemist Chemistry video. Take care. Bye for now.